All right, ladies and gentlemen, this is going to be your AP Chemistry lecture. This is equilibrium, the first lecture in here, and we're just essentially today going to define the concept of equilibrium, what it is. You've got your learning objectives here, so make sure that you are paying attention to those, and we will get to the point to where we're actually writing equilibrium expressions today by the end of this, and you'll understand exactly what all of it means. All right, here we go. All right, so first we're going to start off by defining exactly what is equilibrium. We've all kind of heard it, the word equilibrium before, hopefully, and in your mind you've got a definition of it that's going to be something along the lines of a balance. When you're in equilibrium, you're within some kind of balance, and really that's the heart of what equilibrium is, even in chemistry. And so we're going to take a look at a reaction, and we're going to focus just on this top one here to begin with. I've got my hydrogen plus my iodine gas, and it's going to form 2 moles of hydrogen iodide. And this is going to be my forward reaction. So what I'm telling you here is that I'm heading in that direction. So I'm going to start with initial concentrations of hydrogen and iodine, and I'm going to have no hydrogen iodide to begin with. Now, the funny thing is, as this reaction progresses, what we see and what we inherently know is that the concentration of this hydrogen iodide is actually going to go up. And once it goes up, we have to start thinking about, well, there's actually going to be a reverse reaction that occurs as well. And so what we can do is we can take a look, and based on what we learned in kinetics, is we can figure out what the rate of that forward reaction is. And we're going to, we've got K is the rate of our forward reaction. And then what we do is we can look as the hydrogen iodide, right, builds up, some of it's actually going to decompose back the other direction. So we have to take a look at what our reverse reaction is. Because now you're going to reach a point where this reaction does become non-negligible. How's that? Like, it matters. It's going to reach a point to where I've got such a buildup of hydrogen iodide that this reaction will occur with some appreciable rate. And what we see is that at equilibrium, these two right here, and this will be actually K negative 1, right? Or 1 over K, because they'll be reciprocals. At equilibrium, these are equal, right? At equilibrium. I'm going to put at equilibrium. So at equilibrium, the rate of my forward reaction and the rate of my reverse reaction are the same, all right? And so what we're going to do is we're going to go ahead and come up with a definition of dynamic equilibrium here. I'm going to type it out, so hold on just one second. Okay, so I've got my definition down here, and what we're going to say is that my dynamic equilibrium is actually going to be, oops, sorry about that. My dynamic equilibrium, which is here, is going to occur when the rate of the forward reaction, that's really important, right? It's the rate of the forward is equal to the rate of the reverse reaction. All right? And what most people don't understand, and this is a usual point of confusion, when we are at dynamic equilibrium, we're talking about rates, right? We're not talking about concentrations. Equilibrium doesn't really mean that there's a balance of concentrations per se. So the usual point of confusion is a lot of people will say, oh, well, at equilibrium, the concentrations of the reactants and products are the same, and that's not actually true, right? And so we're going to put this down here too. All right, so here we go. We've got that down there now. So please understand that when we do this, the dynamic equilibrium does not mean the concentrations of reactants, products, and equal. There's a balance between them because of the rates being equal forward and reverse, so there's not going to be any change in concentration, but the concentrations are not the same. All right, so please make sure that you've got a grasp around that. We're gonna address that here on our next slide as well. All right, so what we've got here, we're going to go and relate the equilibrium to kinetics because we're talking about rates of reactions and then we're balancing concentrations. So let's look at a graph that we know, and it's this concentration versus time graph, and we're going to stick with our reaction that we were looking at a second ago. All right, and so I'm going to go ahead and draw a couple of lines in here. My first one is going to be for HI, right? And I know it's for HI, and so this is going to be the concentration of HI. I know it's that product because I start at 0 concentration, right? And so I'm only making this. And then we're going to take a look at the other two, and we're going to say, well, the hydrogen, let's start that out up here, and then we're going to see a decrease. and this is going to be the concentration of hydrogen. And then I'll have another line here. We'll say this line is going to be the concentration of the iodine, right? And so I'm going to say that I started out with 0.8 molar iodine and that I started out with 1 molar hydrogen. So the concentrations, now notice the graphs look the same, or you would expect both of these lines to be on top of each other if we were in kinetics, because the rates of change are going to be the same with them because of the coefficients. So what I did to give yourself 2 lines is I just started them off at different concentrations, but notice the rate of change here for both of these is still the same. All right, and now what I'm going to do is I'm going to go ahead and extend these lines this way, and notice they have flattened out. There's no more change there. And so at some point, you'll notice the concentrations are not changing, right? And so we're going to add another line here, and we're just going to say, you know, if we go ahead and do this, in this area that we've established here, now this is at equilibrium. We're going to say equilibrium has been reached in this area because the concentrations are not changing, right? The rates of my forward reaction is equal to the rate of my reverse reaction, so any hydrogen iodide that's made is also going to, an equal amount is going to decompose to produce hydrogen and iodine again, all right? And so understand, we're still looking at a concentration versus time here, and then this is really important. I'm not going to write it, but I want you guys to write it, that in this area of equilibrium, the concentrations do not change, right? And that's one of the things you say. I wrote down here a couple of things to notice. The first one is that at equilibrium, the concentrations do not change. So write that down, all right? At equilibrium, the concentrations do not change. The graph is going to be a flat line. The next thing is that, and I'm going to go ahead and write this one because I think this is really important, the ratio, right? The ratio, this is the other thing I need you to know, the ratio of, I'll say, my concentration of my products versus the concentration of my reactants is constant. All right, that's an S there. So the ratio of the concentration of reactants and products is going to be a constant, and this is something that's going to be very, very important because this is going to drive our equilibrium expressions, all right? So please understand, at equilibrium, the concentrations are not going to change, and the ratio of the concentration of products versus concentration of reactants is going to be constant, okay? All right, so now we're going to move on, and essentially what we're doing is we're building upon the last thing that we wrote down in the last slide. So as we just saw, the ratio of the concentrations do not change at equilibrium, all right? And we can use this ratio to mathematically describe equilibrium, all right? So we're going to come up with something called an equilibrium expression. This is an equilibrium expression. What we see right here is K. This is my equilibrium constant. Now, something I do want you to notice is that this looks like it's a rate, right? But it's capital. It is a capital K, right? Which makes it different, right? My rate constant was a lowercase k. My equilibrium constant is a capital K. Please do not get those mixed up. It's something that you need to kind of hammer into your head right now, very early on. Your equilibrium constant is a capital K. Your rate constant is a lowercase k. All right, and so now what we're going to do is we're going to finish out the equilibrium expression because we've got just one product, but we've got more than one reactant, so we need to actually stoichiometrically account for all of this stuff. All right, and so here we go. We're going to finish this out, and we're going to say that my K value, my equilibrium constant, is equal to the concentration of my hydrogen iodide, and it's going to be squared. Right? This is almost like kinetics a little bit, the elementary reactions. I'm going to take my coefficient and I'm going to make it squared. This doesn't mean that it's second order because we're not doing kinetics, guys. This just means that I have to account in this concentration ratio that this coefficient is going to be produced twice as fast. All right? And that's essentially what we're saying here when we do this. All right. Next thing, the part of it, we're going to take our reactant. So we're going to draw our line here, right? And then the concentration of H2 times the concentration of I2. And what this is my equilibrium expression. right? What I've got over here, this is my equilibrium expression. The couple of things that you need to know. The exponents are determined by the coefficients. I'm going to take all my reactants and I'm going to put them in the concentration. Now remember, at equilibrium, this ratio is constant, and so this equilibrium constant is going to be constant. All right? Because these values don't change, we can mathematically describe equilibrium just by giving it an equilibrium constant value. All right? And we'll figure out later on how to calculate all this stuff that's going to be involved. But for right now, I really just need you to understand how to set up an equilibrium expression and start understanding what it means, all right? As far as like the ratios are the same, okay? Okay, so now what we're going to do is we're going to write a couple of equilibrium expressions. What happens if K is less than 1, right? What if K is less than 1? Well, let's look at my expression, right? I've got my K value is equal to the concentration of products over concentration of reactants. If my K value is less than 1, that means my products, the concentration is higher, or I'm sorry, is lower than my reactants concentration. Right? Because it's less than 1, the top number would be a small number, the bottom number would be a big number to get this value. And so what this means is if my K value is less than 1, the concentration of products is less than the concentration of my reactants. All right, and that's important. And what that means, essentially what I'm telling you guys is that if I'm looking at my reaction up here, if my K is less than 1, my reaction does not progress very far to the product side. That means I'm mainly going to have reactants at my equilibrium. All right, and so this K value, and this again is not something and I guess I'll go ahead and write it. The reaction does not proceed much towards reactants. All right, so my reaction does not proceed very far towards the reactants if my K is less than 1. All right, now I'm going to look at a situation where my K is approximately equal to 1, right? At this point, again, I've got the same equilibrium expression. My K is equal to the concentration of products over concentration of reactants. Well, y'all know this. If I've got a fraction that's equal to 1, that means these two values are approximately equal. All right, so if my K value is close to 1, that means at equilibrium, the concentration of my reactants and products is about the same. And that's what you really need to understand, right? And so you're going to get about if we're looking at my reaction up here again, you're going to get about a 50-50 ratio here. So it proceeds this way, about half the products or half the reactants are used up and a concurrent amount of products is formed. All right, and so with the K value equal to 1, you need to understand, and I'm not going to write this again because I'm running out of time here, but concentration of products is roughly equal to the concentration of your reactants, right? So understand that. And then the last one that I'm going to put some stuff down here, if my K is greater than 1, again, I'm looking at the same expression, right? Concentration of products over concentration of reactants. And if my K is greater than 1, that means the top of my fraction is larger. So in this particular case, the concentration of products is greater than the concentration of my reactants. And what this means is that my reaction goes towards products. All right, so in this particular case, the reaction proceeds towards the products at a relatively high rate. So at equilibrium, I'd end up with a lot of products and just a few reactant molecules if you want to look at it that way, okay? These ratios are very, very important, guys. You need to make sure that you understand what they mean, what it means if my K value is less than 1, equal to 1, or greater than 1. So make sure you spend some time on this to get it kind of locked into your brain before we move on. All right, this last slide, what I'm going to do is I'm just going to ask you to pause it. I want you to try and write the equilibrium expressions here on your own. And so go through each example, and what I'm going to do is I'm going to pause it, and then I'm going to go ahead and write them out while it's paused, and that way when I press play, it'll pop up and give you the answers for these. And so go ahead and go through and do each one. And then as I come up, I'll explain what we're doing. So pause it, write the 3 equilibrium expressions. I'm going to pause it and put the answers up here, and then we'll come back. All right, guys, so here's the answers. Hopefully you got these correct. Looking at the first one, notice my product is going to be up on top. It's just a C. I don't have any exponent here because the coefficient's 1. I've got the concentration of A. It's squared because of the coefficient of 2. And then I've just got B here with, again, no exponent because there's no coefficient. So it's always going to be, your equilibrium expression is always going to be products over reactants. All right, so look at the next one. I've got D squared and E because the D is a 2, the E is a 1, and then concentration of my reactants is just AB. And then the third one, I've got the concentration of C and D. D is squared because of the coefficient of 2. And then I've got the concentration of A times the concentration of B. B is cubed because of the coefficient there. So hopefully you should be able to write some equilibrium expressions at this point. Go ahead and start working on your practice problem 6.1. And if you get stuck, make sure you're asking some questions. You can either post them onto Edmodo, or you can come to class and work it out with me or some of your classmates. And we'll see you there.